Welcome back, ladies and gentlemen, to another episode of Dave Does Math from Home. This is one of my favorite parts of Calculus 3. Today we are talking about line integrals. So hopefully we remember from all the videos on 17.1 when we talked about vector fields. I mentioned a couple times that the reason we're talking about vector fields, all these big two-dimensional, the entire xy plane is covered with little vectors. You have a function. It takes inputs on the xy plane, gives you vectors on the xy plane as outputs. So you have this whole field. It's covered in vectors pointing in various directions, various sizes. The reason we were doing that is so that we could use vector fields to model the flow of things, or the forces, flow of water across the surface, or forces of, electric force, electric flow, magnetic force, those sort of things. So we're going to use a vector field to model these flows or these forces, and then we're going to look at paths through or across or on that field, and we're going to look at how we can take the integral of all of the work that this vector field is doing as an object moves through a path on this field. So that's what this section is all about. We're going to talk about these line integrals. Line integrals means you have a path through a vector field, and we're going to look at the integral of all of the work that the vector field as a force is doing on this path as an object moves across it. And this is going to involve a lot of steps. Individually, each step is something that we know how to do. We've done it before. So the new material that we're going to be covering here is just how we're going to do it all in one place, how we're going to put it all together in one big thing that we're going to call a line integral. So buckle in. Here we go. I'm just going to start with an example. And the example that I want to start with is, let's say that the vector field we have, f of x, y, is, I'm going to use the toilet flush field, negative y comma x. This is my vector field. Standard issue, counterclockwise, counterclockwise toilet flush. That's that. The path that I want to use, sometimes it's called C, sometimes C for curve, sometimes it's R. I actually don't know why it's called R sometimes. When I was taught line integrals, R was the letter that they used for the path, and I just got really used to that. It might be C or S now. It's changed. But the path is going to be the parabola y equals x squared from 0, 0 to 3, 9. This is going to be the path. So, how do we do a line integral? Before we actually start working at the line integral, the thing that I want to do first is not actually an integral part of the process. I just want to do it first for this particular example because I feel like it might help you understand what's happening and why we're doing what we're doing. So for this one in particular, I'm going to draw a bit of a picture. We have a vector field. It's doing curvy stuff. We have this vector field that's kind of flowing counterclockwise. And across that vector field, we'll do this in red. Across this vector field, we have a parabola. It's going to do this. Here's 0, 0, here's 3, 9. So you can see some of these vectors are going to be kind of like perpendicular to the path, and they're not going to contribute much of anything. They're not going to do any work for or against this path. They're just going to be pushing in a completely separate direction. Some of the vectors are going to be kind of helping us along that path. So when we take this vector, this line integral, we should expect a net positive result. If we had something that was going in this direction, where it was always against the vector field, then we would expect a big negative result. If we have something that was going straight out in a straight line, and it was always perpendicular to this vector field, then you would expect a net result of 0. Something that is generally moving sort of vaguely with the vector field, you expect a positive result. This is mostly sort of neutral to it, it's mostly perpendicular, but it's a little bit with the vector field, so we should expect a small positive number. Here's how we figure out exactly what that small positive number should be. The first thing we need to do, we can do line integrals in 5 easy steps. This is money back guaranteed. This is patent pending, copyright 2005. I don't remember when I came up with this, but line integrals in 5 easy steps, guaranteed. The first step is we need to parameterize the curve. This business here with y as some function of x, that's not going to cut it for us. Ultimately we want to take y and x out of this completely, which is why we spent a chunk of Calc 2 talking about parametric equations. We're going to transform this curve into a parametric equation. That way it can wiggle around however it wants on the xy plane. It can do whatever kind of shapes and wiggles it wants, as long as it has one dependent variable, and that variable is t. So we're going to swap out all our x's and y's for t. And there's a couple different ways to do this depending on what kind of shape you have. If you have a circle or part of a circle or an ellipse or part of an ellipse, then the way you're going to parameterize that is with sines and cosines. If you have a straight line between 2 points, then you can parameterize that using basically just the difference between them. You'll attach a t to it. That's very simple. If you have a function like this, then you want to parameterize this. The super duper easy way to parameterize this is to say whatever this dependent variable is, you say that that equals t. So we're going to say x equals t. This is the first part of my parameterization. And we're going to say if x is t, then y is t squared. There you go. This is our parameterization of the parabola y equals x squared. We need a starting and ending value. If we want this thing to start at 0, 0, then 0 is one endpoint for t. If we want it to end at 3, 9, then 3 is the other endpoint for t. So t is going to go from 0 to 3, and that'll take us from the point 0, 0 in x and y into 3, 9 for x and y across this parabola. You can always do this if the curve you're given is represented as a function. You can always set x equal to t, or whatever dependent variable they give you here. Or sorry, whatever independent variable you have here. Set the independent variable equal to t, and then y is the other variable, and now you have parametric equation in terms of t. You just need to do the endpoints. So that's step 1. Step 2 of our line integrals in 5 easy steps is we need to find, so I'm going to say, again, I think the book does this a little differently, and I'm not sure why. I was always taught that when you're doing these, the curve you get is r. So we're going to parameterize the curve r. Oh, I guess I'm not quite done here. I should write this curve as a vector. So if x equals t and y equals t squared, this is r. Or let me write this as r of t. R of t equals t comma t squared. This is the path as a vector. And so you can think about this if you plug in various numbers for t. Like if you plug in t equals 2, let's say, this will give you the vector 2 comma 4. So technically this is a position vector. It's telling you how to get from the origin to the point 2, 4. That's your position vector. So this is a series of position vectors that always go from 0, 0 up to the point that you're interested in. So when t is 2, it'll take you from 0, 0 to 2, 4. When t is 3, it'll take you from 0, 0 to 3, 9. This will just give you an increasing series of position vectors, basically. We're not going to use these position vectors. We are very interested to find out little tiny pieces of these position vectors along this path. So we don't want the whole thing that goes from 0, 0 to 2, 4. We just want the little tiny pieces of it at 2, 4. So to do that, once we have our r, we're going to find dr. dr, hopefully, is exactly what you'd expect it to be. The derivative of r is, you take the derivative of this, that's 1. You take the derivative of this, that's 2t. That's it. We can slap a dt on the end of that, just because the chain rule. If you forget the dt, I'm not going to be super mad about it. I forget the dt half the time myself. This is dr. It is this parameterization, this vectorized parameterization of our curve. Then you take the derivative of it, and that's step 2. I goofed up that 2 pretty bad. This is meant to be a 2. Okay. That's all there is to step 2. Step 3. We're going to ignore dr for a minute, and we're going to express f in terms of t. So right now we have a vector field f, and that is expressed in terms of x and y. And again, we are not interested in using x's or y's here. We want everything in terms of t. That's the goal. So we're going to take our f, and we're going to replace our x's and y's with these things. So I know that y is t squared, so f of t should be negative t squared, and then x is just t. So this is my vector field expressed in terms of t. This is what the vector field is doing along this path. And this is a simplification of this vector field. This only works on this path, but on this path is the only thing I care about. This thing won't tell me what the vector field is at the negative 3, negative 1. You can't make these things be negative 3, negative 1. Not really. Not in this scope of t. But that's fine. I don't need it to be negative 3, negative 1, because that's not on my path. This will tell me exactly what all the vector field is doing along this path and nowhere else, and that's what I want. So, I have my vector field in terms of t. I have tiny little pieces of this path through the vector field. The next step is where we combine these two things. We have two vectors here, and hopefully you were listening when I was talking about how this thing is going to work. We said earlier that when these things are perpendicular, there's very little happening. If you have a path that is always perpendicular to the vector field, then the line integral should be 0. And if you have a path that's pushing in the same direction as the vector field, then you'll get a big positive number. If you have a path that is pushing against the vector field, you'll get a big negative number. Hopefully we recognize all of that description as the dot product. We want to take the dot product of the vector field to see how much of this vector field is in the same direction as the tiny little pieces of our path. So, step 4 is find f of t dot dr. This is the dot product of your vector field expressed in terms of t and your tiny little chunks of the path. So for us, that's going to look like f of t dot dr should be dot product is you multiply corresponding pieces, so negative t squared, you add them together, plus 2t squared. We can simplify this a little bit. This dot product is just going to be negative t squared plus 2t squared is t squared. This is the dot product between these two things. And now, I promised you a line integral, and so far we haven't actually done any integrals. So step 5 is integrate. Oh, hey, you remember that time when I said I forget the dt half the time? Yeah, technically there's a dt here, because it's part of dr, and I just forget about it all the time. Which is okay. As long as you remember that you're doing the integral of this thing with respect to dt, then you're all set. So, we have the thing we're integrating. In step 5, when we integrate, the integral of f of t dot dr is the integral, I should say along the path. No, I forget how this, I think when the book does it, I feel like the book writes this as the integral along the curve of like big bold F dot ds, I think. I don't know. I'm going to call it the integral, sure, we can call it the integral along the curve of f of t dot dr. This is the integral from 0 to 3, those are our bounds on t, of t squared dt. Which is 1/3 t cubed from 0 to 3, which is 1/3 of 27, which is 9, minus 0. The answer is 9. When we started this, we expected a small positive number, and I submit that 9 is a pretty small positive number. So, depending on what these things represent, if it's magnetic fields or electric flow or the path of an ant in a stiff counterclockwise breeze, I don't know. You can put units on this. Usually the units you attach to this are units of work, because the vector field represents a force and the path represents a distance, and so when you multiply them you get a unit of work. Work is force times distance, and then you integrate it and it just adds up all the little pieces of work you do at all these tiny little steps, and you get the total work to move from here to here. Or not the work that you have to do, it's the work that the vector field does on an object moving along this path. So the work that you have to do might be a little different, but the work that the vector field does on the object is represented by this line integral. So that puts us right at 19 minutes, so I'm going to shut this video down. We'll do another one. I've got a couple more examples to go over. More examples of different kinds of vector fields, more examples of different kinds of curves to parameterize. But write down these 5 steps. These are the 5 easy steps. They will be good to you. Remember the 5 steps. Guaranteed to work, or your money back.